Hello all and welcome. So this is an introductory video for a series of videos that are targeted towards magnetic components for SMPC, switch mode power converters as we say. Basically, in these tutorials I would like to concentrate on the design aspects of inductors, transformers that we are going to use in switch mode power converters. So let's begin our discussion with very basic concepts, which will set up the stage for us to move forward in the design of magnetic components. So, from the fundamentals, let's start with a infinitely long conductor, which is carrying some current I, and without any equations itself, we can say from the right hand thumb rule that the flux lines will be flowing like this, right? So let's go a step ahead and try to calculate what is the B field at any given point, uh, with, which is at a certain distance from that particular conductor. So this was given by Biot Savarla, and these two are French mathematicians, as you can. This is Biot and this is Savart. So these two combinedly given us a handy equation which is analogous to the Coulomb's law in case of static electric fields. Now we are talking about magnetostatics, right? So this formula is equivalent to Coulomb's law, which in which this is the source and it is the proportionality relation between the distances between the source and the point where we are trying to compute magnetic field. So due to this small element dl, what is the magnetic field over this point P is our point of interest, so that can be found out by this particular equation. And since it is in its differential form, we can go about and do the integration and find out B as a function of radius r. So I would say this is my coordinate system here. Okay, that is the origin, and so this is one thing. And let us see these kind of straight conductors we usually see in transmission lines. Rather, now we are focused on designing inductors and transformers, so usually we make turns out of these um, conductors, right? Even here we assume there is a written conductor which is not shown here. So when we go for a change in geometry like this conductor, as you can see here, it's a circular ring and some current I is trapped inside it. So from the same right hand thumb rule, we can predict how the flux lines will be going and surrounding it. So here we have some flux lines passing to the center, some flux lines very close to the ring, and we can make this stuff without any difficulty. So the difficulty comes when we try to quantify things again. So this is the surface which is I'm talking about, which is being linking. So whenever we are talking about a closed loop, we should also keep in mind what is the kind of surface it is making out. Like, so here it is the surface into which these flux lines are linking. So these are the flux lines that are linking, right? I just removed the conductor and I'm just representing the surface here. Now we know that the generalized equation, I mean with this particular equation right over here given by Biot and Savart, is sufficient to calculate magnetic fields for any given geometry, but it requires some simplification, some substitutions or change of coordinate systems to make the problem easy. So right now here we can write a similar equation for dB bar is equal to the small element, this element which is equal to I into r into d theta, and the position vector. So it is the same thing. The point here I want to mention is it's not about the math right now. We are setting up a problem. um, we are showing that it is a involved uh, in mathematics, right? Because solving for a magnetic field at this point, which at this point, let us say at this point, is difficult. Why? Because it does not have any symmetry. But if you try to calculate magnetic field on the z-axis, it will be having symmetry, because if you take like this, on this particular point, if you want to calculate the magnetic field, so this magnetic element will have an opposite element over here, and it is having symmetry. So using that symmetries, we can calculate the B field at that point. But if you try to calculate at any other point, it is difficult. There is no such simplification. Okay, so that's how it is. And now we usually, when we try to make an inductor, we usually go for multiple number of turns. So when we go for multiple number of turns, let's see how the surfaces will be. And so from our basic understanding, we can again draw the magnetic flux lines using right hand thumb rule, and we can see how the flux lines are linking to those surfaces. And yeah, so this is pretty much it. Like and we can see that the surface is highly complicated, right? This surface is highly complicated. How? Like if you want to imagine a surface for this helical structure, just try to imagine placing a spring inside a soap lotion or soap solution, and take it out. You will find a surface that is attached to these to the spring walls, right? So that is the kind of surface we are talking about. And so these are the flux lines. It is fairly straightforward right here. Now let's bring in magnetic material. Okay, this is the magnetic material I'm talking, which has higher permeability, magnetic permeability than air. When we place something like this, something interesting will happen. So all the flux lines will now start to go in a uniform fashion inside this magnetic material. Okay, something like this, right? And previously the flux lines are diverging a lot, even at these locations, but now somehow the flux lines are confined in the space, right? That we can see. And one more point here is this solenoid, which we call will produce a similar magnetic fields to that of a permanent magnet. Just to bring out the similarities between these two are equivalent. Isn't that interesting? So yeah, let's move forward and see what will a magnetic circuit do to us. Like so sorry, here this should be the magnetic circuit. And yeah, when we place the conductors on a magnetic circuit of area of cross section A, it is fairly simple. Previously we have seen a very complicated equations like this for the magnetic field, right? Now it is not the case. And we have this B is equal to phi by A, or when you write it in the integral form, the flux that is passing through the area A is given by integral B dot ds. So since the magnetic flux lines are becoming uniform inside, I'm saying it uniform with a quote on it. Okay, B is uniform. We have to take this with a pinch of salt. because it's not exactly uniform, but for engineering purposes we can assume it to be uniform. So whenever this field is uniform with respect to the space, then I can bring out the B from the integral and just write it as this. So now this surface area, the integral of this surface area is nothing but the area of cross section of the core, right? So simply I can represent B in a very simple, it boiled down to a geometry. Previously there is no geometry. It is very difficult to calculate the magnetic field or flux that is passing through, let us say, this surface. Okay, so you need to know the function b of r comma theta or whatever coordinate system it is in. Then you need to integrate it with respect to the ds. So usually for these kind of problems we go with what we call as FEA, finite element analysis, and maybe in future videos we'll see some of it, like the simulations for some of the circuits, magnetic circuits. Now let's bring in some simple mathematics into it, and these two gentlemen, um, Ampere and Maxwell. Ampere is also a French mathematician and physicist, and Maxwell is an English scientist, as we all know. So basically what I'm trying to bring in here is Ampere Circuit Law, is what we call Ampere Circuit Law. But basically it was proposed by Maxwell, and it is sometimes referred to as Maxwell Ampere law. So why I'm bringing this, it will be clear just in a moment. So what does the law say? If there is a conductor and if you take a contour around that conductor, and that contour will form an open surface S0. Okay, so on this contour can be of any shape. Okay, it is our choice. Usually we take a contour shape which makes our life easy, like which will bring out the equations simpler, but the contour shape can be anything. Okay, so for this contour I am attaching this open surface. When some current flows through this contour and it pierces this surface, then if I integrate H, magnetic field intensity, along with the elemental length dl over here, and this representation is nothing but this contour C over that contour, that will give us n into I enclosed. Why I am writing n here? Because it is in general. We will easily see this in when we talk about spiral coils. Okay, here it is just I enclosed. Whatever I that is entering here, that is what the right hand side will be. Okay, so the idea here is to bring the characteristics of the material. Okay, so let's see how we can bring it out. Now when here I am representing, this is a transformer, and this is the primary, this is the secondary. As you can see, the secondary is open, that means it is no load. When it is under no load, I can apply Ampere Circuit Law. Then what is the best contour that I can choose? So the best contour that we can choose is some this is the path, the flux line itself is the contour. Okay, so and as you can see, the open surface which I have drawn here for this contour would be the back side of the screen. Okay, it's maybe I'll draw it. It's something like this. Okay, yeah, so this is the flux line, and on that contour we are trying to apply Ampere Circuit Law. Now, so what So this particular surface is being pierced by these n number of conductors, right? So that's why we write integral h dot dl is equal to n1 into I mag. Why I am calling it as specifically I mag? Because since the secondary is open, whatever current that is drawn by this primary is nothing but magnetizing current, the current that is required to magnetize the domains inside the core magnetic material. So let's I think it's fair enough, right? So h is uniform, as we have discussed. Since b is uniform, h is also uniform, so I can bring it out of the integral, and so that particular surface or the contour is enclosing I n1 into I mag uh, is the enclosed current. Now from that I can find out what is the h, right? And let's move forward and see how we can calculate b. And why we are doing this? We want to relate b and h. We want to see how b and h are related. That's what we are going towards. So in order to find the b, let's bring in Faraday's law, right? He's Mr. Faraday. He is also an English physicist, and Maxwell is his student. So we know this equation. This is very well known equation. From that we can write that the flux linkages, where this psi is the flux linkages, is nothing but the integral of the applied voltage and with respect to time. If it is a sinusoidal voltage, then the flux linkages will also be sinusoidal, right? So let's apply that, and from that we can know what psi is for applied voltage. But from the geometry we know that the flux is nothing but B into AC, right? That's what we have discussed earlier. AC is the core area of cross section. So from that, if I multiply with N1, I'll get the flux linkages on the primary. Now we have some equations. This is equation 1, let us call, and this is equation 2. Okay, so we have two equations which has magnetic flux density and magnetic field intensity. So what is the relation between these two, one can ask. For that we can do a simple experiment from the physical laws that we have discussed till now. Okay, so let us take say this is the specimen which you want to test, which has n1 turns in the primary and n2 turns in the secondary. I am applying a sinusoidal voltage right here, V1, and the core is drawing I mag. Why I am saying it as magnetizing current? Since even though it appears that the secondary is loaded, basically this circuitry is a high impedance circuit. Okay, something like an op amp, let us say. Okay, so the secondary is almost it's not loaded at all. Then from our equations, if we sense the primary current of this coil and just pass it through a gain block of N1 by Lm, I forgot to mention, is the mean length of this contour. We are taking the mean length of this core. Why only mean length? We can take any path, right? We can take any of that, but mean length gives us a better approximation of whatever we are doing. It works well with the assumption of taking B as uniform. So if we pass that current from this gain block, what we will end up? We will end up in H, right? Whatever quantity, whatever signal we get over here is nothing but magnetic field intensity. And in the secondary, we sense the voltage and integrate it. As we have seen from the Faraday's law, we can get the flux linkages by integrating the voltage, right? So if we integrate the voltage, then we can get flux linkages. Once we get the flux linkages, we know the relation how to get the B from the flux linkages for a given geometry, right? It has some core area, and from that if we want to take bring a magnetic flux density, it is psi by number of turns and area of cross section. If we just pass that signal through this gain block, we will end up with B. So just feed these signals to an oscilloscope's Y channel and X channel. This is B, we are getting into the Y channel, and H we are getting into the X channel. So we will end up getting the BH loop or the BH. Why we are forming a loop here? Because of the sinusoidal or periodic signal that we are applying here as an excitation. Here it is an periodic signal. So we end up with the characteristic loop or characteristic property of the material. So once we obtain it, we have to pay some attention here, right? We have to describe different materials will have different nature of BH relation, right? So when first the material is being magnetized, this is the path through which this is the path through which B and H are related. After that, once it got magnetized, it enters into this hysteresis loop. Okay, so there are some significant features of this particular BH loop. First of all, it is interesting to note that B and H, how they are related. Is this loop is a single valued function? No, it's not a single valued function. It is very difficult to represent the exact relationship between B and H since it is not a single valued function. But this particular magnetization curve is a single valued function. So when we see that, when we write B is equal to mu H, we are referring to the magnetization curve, right? And yeah, let's discuss some features of this particular curve. When H is increasing and B starts saturating after a particular value of H, and it cannot go beyond a certain value. It is interesting to note that let me draw B and H's magnetization curve here, maybe in the side. Yeah, let's just focus on the magnetization part. So when I'm trying to magnetize, this goes this way, right? And we are showing it as B sat. But here, let me be accurate here. It will have a slight slope like this. And again it will have the maximum slope here, and then it will start saturating, and it will still have some slope basically. Okay, and what is this slope is nothing but mu naught. Okay, since once the magnetic material is completely saturated, there are no more domains to align, right? So whatever that is there is the vacuum. So the final slope of the BH curve is nothing but the slope of vacuum. Here it will have some mu naught into mu r. Okay, so from this magnetization curve we can write B is equal to mu into H, where mu is equal to mu naught into mu r. Again, mu r is nothing but a function of H, right? It is not just a number. If you are in this region, maybe you can approximate it with some high value of number, but basically it's not a single slope. Its slope itself is changing. So that's about the magnetization curve. Let's come to the B sat and this particular point, let us say we call it as K, let us say. Okay, so this is the retentivity, the property when you remove all the excitation, still there is some magnetism left inside the material. You need to give extra energy in order to bring it back to zero magnetic field. So this we call it as retentivity, and the difference between these 2 points we call it as coercivity, and that is the magnitude of current that you have to, magnitude of H that you have to apply in the reverse direction in order to bring back the magnetism to zero. Okay, so basically these are the two important things we can discuss about uh, the BH loop. We call this as hysteresis, and basically hysteresis is everywhere. We can find hysteresis in all practical systems. Just to give a look, just to give an overview of hysteresis, let me just walk you through the hysteresis Wikipedia page, right? So, sorry, it was okay. So hysteresis is very general. You can go through this page, and I just want to bring out the fact that it is a very common phenomena. It appears in controls, it appears in electronic circuits, aerodynamics, mechanical, and elastic properties of the materials. Lot other stuff. Magnetic hysteresis is just one one magnetic property of the material, or I can say one non-linear property of material. So let's go back to our discussion, and based on this hysteresis loop or BH loop, we can classify materials. Okay, so the materials with very low coercivity, we call them as soft magnetic materials. The materials which have which has very high coercive forces required to demagnetize, we call them as hard magnetic materials. We generally use hard magnetic materials in cases where we require permanent magnetism, right? So it is very difficult to demagnetize those materials. That's why we can call them as hard magnetic materials, whereas soft magnetic materials is what is going to be our interest in the next few lectures, since this soft magnetic material will have a very low uh, loop area as compared to the hard magnetic materials. Okay, we'll come up to the point where why loop area is important, but right now this is what is our primary focus for